Hello everyone, this is Aditya and today we'll discuss Euler's theorem for homogeneous function and we'll see the derivation part because we have already covered the function several variable in a different one shot. So I had left the derivation portion at that time, so that is why I'm covering it right now. So please do like, share, subscribe my channel and please support my channel. And now let's start with the derivation. So first of all, let's see what does this theorem states. Well, let's see. So suppose you have a function f x comma y is suppose equal to z. Z is some other function. So f is dependent upon x and y, right? Which means x and y are two independent variables, right? Okay. So what does this function states? Obviously, this is for homogeneous function. What is a homogeneous function? For example, f of x comma y is suppose equal to x square plus y square plus upon x minus y, right? Okay. From the numerator, you take x square as a common and you get y square by x square. And from the numerator, you take x common. What do you get? 1 minus y by x, right? You will get this, okay? And you get x into 1 plus y by x whole square and 1 minus y by x whole square. And what you get? You get x to the power 1 into some function phi of y by x, right? You get this? And notice that this phi is a function of y by x, right? So any function which can be expressed as a product of one independent variable into another function of y by x or x by y. This could be written as y to the power 1 into some other function, suppose g of x by y. You have to take y in that case common, right? I hope you're understanding what I'm saying. So basically, such functions are called homogeneous function, which can be expressed basically in terms of y by x or x by y, right? Okay. So now we know the property of f of x comma y. So now we are ready to apply the same, right? And notice that you have a variable over here x and here also y. But notice that both of them have a same power, that is 1 over here. And 1 is basically telling the degree of the expression, right? The degree of the homogeneous function. So in this case also we assume that f of x comma y is a nth degree homogeneous equation, which means if it is a nth degree, so f of x comma y can be expressed as x to the power n into phi of y by x, right? Okay, where n is the degree. Yeah, okay. So we will apply this idea and we will solve this and we will prove the expression. Okay, so let's see what we are going to do. Let me erase this. Okay, okay. So we know that f of x comma y can be expressed like this. In fact, you could do like y to the power n into phi of x by y. Both are same, but I'll be sticking to x, right? Because we are familiar with x a lot. Okay, so z is equal to f of x comma y. Okay, you can write it like this. And further, we all know this. So let me write it over here only. X to the power n phi of y by x, right? So we have another expression for z, right? Now the derivation will start. Okay. So let me write it over here. Okay. So if we differentiate with respect to x first of all, right? So z is equal to x to the power n phi y by x. So will it be easy to first of all differentiate with respect to x or y? Well, I see that there's only one y expression, that too in the function, so we can approach it using the chain rule. So I feel it is easier to first of all differentiate with respect to y. So let's do it. So del z by del x, del y actually, and why I'm using a del operator over here? Why not d? Because over here we are dealing with the several functions, so that is why we are assuming x to be a constant and after that we are assuming y to be a variable, and that is why we are differentiating with respect to y keeping x as a constant. So that is why we are writing it like this: del z by del x. I mean del z by del y. Okay, and it is equal to sorry, I am a bit unwell, so that is why the derivative of the outer function, I mean this function phi y by x. Then by the chain rule, we will apply the chain rule in this function, and you will get 1 by x, since the derivative of y is 1, right? Okay, so you can write it like this: x to the power n minus 1 phi dash y by x, right? Okay, so del z by del y is equal to x to the power n minus 1 phi dash of y by x, right? And you can multiply both sides by y. Okay, don't ask me right now why, because we will see it later. You all know the formula basically. That is why we are trying to approach that formula using this pattern, right? So let me write this expression somewhere. Let me write it like over here. So we have y del z by del y is equal to y x to the power n minus 1 into phi dash of y by x, right? Okay. Now let's do the same thing but with respect to x now. Okay. So let's do that. Okay. Let me erase this. Okay. Okay. So now let's see for with respect to x. So del z by del x. Now again we are keeping y as a constant. So you're getting and now you have to apply the product rule even, right? Because there are two places where which you have to differentiate with respect to x, right? Okay. So first of all, with respect to this, it will be nx n minus 1, right? Simple. Y by x, right? You get this thing plus x to the power n as it is into the derivative of this function y by x, right? Okay. Then the derivative of the inner function. What is the derivative of 1 by x? 1 by x derivative, it can be written as x to the power minus 1 derivative, which is equal to x to the power minus 1, and then minus 1 outside, you get minus 1 by x square, right? This is the derivative of 1 by x, right? So that is why you get negative y by x square, since you don't need to differentiate y because y is a constant, right? So you leave y as it is, okay, in the case of chain rule. Okay, let me erase this. Okay, now let's see. Okay, so del z by del x is equal to nx n minus 1 phi y by x plus, or I should say minus, because this minus will go over here, and we get x to the power n by x square is equal to x to the power n minus 2, right? X to the power n minus 2 into y phi dash y by x, right? You get this thing. Okay, now multiply both sides by x, right? Okay, so x del z by del x is equal to n x to the power n minus 1 into x is equal to x to the power n, right? Okay, simple. Phi y by x minus x to the power n minus 2 into x is equal to x to the power n minus 1, right? Simple. Okay, x to the power n minus 1 y phi dash y by x, right? You get this expression. Now let me write it over here. Okay, so now let's add both the expressions. Let's see what we get. So we had got y del z by del y is equal to y x to the power n minus 1 phi dash y by x, right? And x del z by del x is equal to n x n phi y by x, right? Minus x to the power n minus 1 into y phi dash of y by x. And notice that this expression are same, this is equal to over here y. If you write this and this are exactly same, this portion, which means we can write this in place of this, right? Let's write that x del z by del x is equal to n x n phi y by x minus y del z by del y. So you bring this over here, you get x del z by del x plus y del z by del y is equal to n x n phi y by x. And notice that x to the power n into phi of y by x is equal to f of x comma y. So you get n f x comma y. And what was z? Z was equal to f of x comma y. So let's, instead of writing x comma y, because we all know that it is that, I'm removing this. Okay. So we get x del f by del x plus y del f by del y is equal to n times this quantity. Hence proof. Right. So I hope that you all learned something new in this video, and you all like the content. So please like, share, subscribe my channel, and bye bye. Take care.